Thank you for giving me this opportunity. I'm honored to be here to present my recent study about the convective cell characteristics with different aerosol environment. This work is under the collaboration with several institutes, but mostly working with the Colorado State University supported by DOE ASR. So first, I'd like to start with the cloud dynamics and microphysics. Little bit. Cloud microphysics and dynamics control the cloud evolution. This figure is a great figure showing the several microphysics and dynamical processes in liquid water phase and mixed phase and ice phase here. As you can see here, microphysics and dynamics are very interactive with each other and then resulting in the complex precipitation processes. For example, updraft control the particle size distribution, not only raindrop size distribution, but also ice nucleation, global size distribution, and also the ice crystals near the cloud top. And then these also influence vertical air motion through loading, latent heating, or radiative forcing. And in addition, here, aerosols play the also important role to modulate these processes, but impact is still unclear. Remote sensing measurements, such as radar measurement, particularly for my area, is very effective to estimate the cloud and precipitation particle characteristics, but aerosol impact is difficult to measure. So there are several aerosol processes that impact cloud physics. First one is increase in cloud condensation nuclei, CCN, and also it impacts the cloud size distribution. In the polluted environment, more aerosols produces more CCN. The right figure here is the relationships between CCN in x-axis and aerosol optical depth in the y-axis, which represent the number concentration. You can see when CCN concentration increases, aerosol optical depth also increases. So the more CCN result in the more number concentration of smaller droplets, cloud droplets. This is a good observational evidence of the aerosol impact. Left inside is a satellite image over the ocean. As you can see, the several open cell structure of the shallow cumulus over the ocean, but also you can see the white tracks, which is corresponding to the ship tracks. Here. Figure in right-hand side shows the retrieved cloud effective radius. As you can see, the white tracks correspond to the blue colors, which is a small effective radius of the cloud. This cloud distribution also impacts the cloud lifetime. In the clean environment, we could have some larger cloud droplets with lower number concentration. The larger cloud droplets could have a more chance of collision coalescence, producing raindrops quickly precipitating. On the other hand, for polluted environment, the smaller cloud droplets could have less chance of collision coalescence. Cloud droplets persist in the atmosphere, resulting in the longer lifetime of cloud, which also result in the increase of cloud albedo. Aerosol processes in deep convective cloud is a little bit complicated. This figure shows convective invigoration process by aerosols. This is a cloud evolution for pristine environment, clear environment in the top, and polluted environment in the bottom. More cloud droplets could provide more chance of liming, which is icing. Icing can contribute to release of latent heat, which result in more updraft, meaning stronger convection and deeper convective cloud. This is a convective invigoration. The deeper convection is also influence lightning activity. So this is a little bit complicated. Okay. Right figure here shows the relationships between CCN versus cloud top height. As you can see here, the more CCN could have more echo top height, deeper convection. The deeper convection could produce more chance of lightning activity. Each plot shows the time versus height cross section of lightning activity for individual convective cells for a specific CCN environment. Specific Cape environment. When CCN number concentration increase, lightning activity also increases, regardless the Cape, right? So more liming producing more global and more charging, resulting in lightning. But the recent study showed, aerosol impact in the deep convective cloud is very complex, more complex. This is a schematic image by the recent study. These are the modeling studies, and including several processes impacted by aerosols, evaporation, condensation, aerosol entrainment, collision coalescence associated with aerosols. Ice nucleation is also impacted by aerosols, entrainment, updraft, downdraft, and then there's a precipitation particles in the lower atmosphere. These are interacted each other, and also each of them impacted by aerosols, making the process complex. These processes are not represented in the models well. The recent study by our colleague, the collaborators, showed the large variability in the models. This is a result of the intercomparison studies using several models for simulating one case with a different aerosol environment. The figure shows the vertical distribution of cloud droplet mean diameter in micrometers. Solid line represents the simulation with low CCN environment. Dotted line represents simulation with the high CCN environment. Basically, as you can see, in high CCN environment, you can see a smaller droplet diameter, but there are large variability between the models and the microphysics. This also shows the variability in the latent heating. Each panel shows the height versus time cross-section of difference in latent heating as a function of convective cell evolution. Red color represents the positive feedback of the aerosols, and blue represents the negative feedback. So some models like RAMS and Wolf spectral beam models show some negative impact of aerosols, but some of them show red colors more. But they are also associated with changing with the cloud life cycle. They are very complicated. So in this study, even though they are very complex, I focus on the raindrop size distribution as a result of all of processes. Questions I will address are can we observe impact of aerosols on the raindrop size distribution, DSD? And how are DSD changed with aerosols in models? Okay, here I'd like to introduce some two field campaigns for convective clouds and aerosols in Houston. First one is naming tracking aerosols convection interaction experiment, TRACER. TRACER field campaign is supported by DOE arm, and we deployed the mobile facility, including sounding measurement, aerosols, vertical pointing, remote sensing like radar lidars, and distrometer measurement. Nearby the Houston area here. This is the Houston metropolitan area. We deployed the mobile facility here. And also we deployed C-band polarimetric radar here, south to the Houston area. This field campaign is also collaborated with the other field campaign, naming experiment of sea breeze convection, aerosols, precipitation, and environment. We called it SK, led by the Pavlos. This is supported by NSF. In this field campaign, we deployed mobile trucks, 2 mobile facilities, like here, to chase the convective cloud. We deployed not only here, but also we deployed several locations based on the convective cells. The facility includes phase array radar, soundings, vertical pointing, remote sensing measurement, radar and lidars, and precipitation particle measurement as well. We also deployed another C-band polarimetric radar from CSU at the same location of DOE mobile facility here. In addition, we had aircraft observations for the in-situ measurement of aerosols, particle velocity, particle images, and probes in June. We had many observations here, but in this presentation, I just focused on the radar measurement and modeling study. During the field campaign, we conducted very unique radar observation for real-time cell tracking. We had a C-band polarimetric radars, and these radars were tracked one convective cells in real time. Here is a schematic image of the radar measurement. The next radar nearby the Houston area did a very normal observation, like surveillance PPI scan. We selected target convective cells based on the several criteria from next radar measurement. Once we found the one convective cells, 2 radars focused on one same convective cells to scan the high resolution vertical cross-section measurement here. Particularly, our C-band polarimetric radar CSAPA2 performed 3 sector PPI scans and 4 or 6 RHI vertical cross-section scans every 2 minutes, just to focus on one single convective cells. Right figure shows some example images of tracking convective cells. You can see some PPI horizontal cross-section scan every 2 minutes here, and corresponding RHI vertical cross-section scan on the right column here. you can see quick evolution of radar reflectivity structures. You can see the black region here and down, going down, and middle part and going to bottom. So we have a nice quick good observation for quick evolution of convective cells. These are the frequency distribution of sampled convective cells during the field campaign from 4 months. Most of convective cells are observed in the afternoon time over the land associated with the sea breeze. Here I like to present how convective cell characteristics are defined. I listed radar parameter used to characterize convective cells. First one is radar reflectivity, Z. Reflectivity is sensitive to hydrometeor particle size and also number density. Particularly, this is very sensitive to large raindrops. Vertical extent of strong reflectivity, let's say 50 dBz, is a good signature of strong updraft. Second parameter is a differential reflectivity. We call it GDR. GDR is also sensitive to the particle size, not number density, just the size. If we observe this variable in the ice region, this can represent the wet global and hail signatures in deep convection. And also particularly, this is sensitive to large raindrops in the rain region in a warmer temperature. As Michael presented a couple weeks ago, vertical extent of GDR, called it GDR current, is also good signature of strong updraft. In addition, specific differential phase, KDP, is also good signature of strong updraft if we see the vertical extent. The KDP is more sensitive to number density rather than size, and also sensitive to the hail and global signature in deep convection. And then here, I classified collected convective cells into the deep convective cells and shallow convective cells based on the reflectivity ecotop height. Deep convective cell is a 30 dBz ecotop height exceeding 5 km altitude during the lifetime. And shallow convection didn't exceed the 5 km altitude, meaning mostly warm rain process, but deep convection include ice phase process too. So I didn't say, in this study, I'd like to present the characteristics only for deep convective cells. And next, I'd like to introduce how raindrop site distribution is defined. Raindrop site distribution is well expressed by gamma models like these. Here, N is the number concentration, D is the particle diameter, and 0 is the intercept parameter, mu is a shape parameter, and gamma is slope parameter. Here there are 3 parameters, yeah, and then they are converted to the normalized gamma distribution like this, where NW, we call it a normalized intercept parameter. D0 is the median volume diameter. This NW and D0 are very good parameter to explain particle size distribution, meaning size and number concentration. D0 median volume diameter is defined like this, which is sites where the rainwater content is high. Normalized intercept parameter can be explained like this using the zero density and rainwater content. This NW and D0 are estimated using polarimetric radar measurement in this study. D0 can be estimated using empirical equations proposed by the previous study. This is relationships between GDR in x-axis and D0 in y-axis. This is based on the ground-based measurement, ground-based particle 2DVD, video distillmeter measurement, and scattering calculations. And then we can get the relationships like this for smaller GDR and larger GDR. And W, normalized intercept parameter, can be also used estimating using these relationships. These relationships are evaluated well using the ground-based measurement in my previous study. So, okay. And these relationships were applied into rain region only, classified using polarimetric radar measurement. This is an echo classification technique result using polarimetric radars. Top plot shows the vertical cross-section of radar reflectivity for single convective cells. And bottom shows the echo classification using polarimetric radar measurement. For example, red and yellow region represent the isophates, including crystals, global, and hail. And green and blue region represent liquid phase like rain and drizzle. In this study, we applied the relationships to estimate D0 and W into the liquid phase only, green and blue area here. Next, how the aerosol environment is classified. The aerosol number concentration from the SMPS measurement is used to classify the aerosol environment. Top right is an example plot of diameter versus time cross-section from single day. This is 0 UTC and 12 UTC. On y-axis is a diameter. As you can see, number concentration represented by color shows very large variability with time, and also variability in size as well. So I tried to investigate the number concentration with different time period and different size. Bottom plot showed the normalized frequency distribution of number concentration with different size range and different time range as well. Thin three lines represent the all size, and thick line represents the number concentration greater than 50 nanometers in size. Because CCN is contributed by the larger aerosols. Here, I just focus on the large side here. And also, our convective cells are sampled in the mostly evening and afternoon time. We focused on the particle size, aerosol concentration in the afternoon time. This is a classification result. We classified the low aerosol environment at the number concentration less than 970, which correspond to the 25% in the frequency distribution. In high aerosol environment, It's classified as the greater than 2,000 cubic centimeters, which correspond to the 60 percentile. And then we collected 174 deep convective cells for low aerosol environment and 123 for high aerosol environment. We also collected the shallow convective cells, but here I focused on the deep convective cells only. I checked the bias associated with local environment other than aerosols. Here, the frequency distribution of detection time, cloud depth, 30 dBg ecotop height, and K for the samples convective cells with different aerosol environment. High aerosol environment in red and low aerosol environment in blue. Fortunately, there are no significant biases in detection time, cloud depth, and Cape environment. And then we investigate the statistical characteristics of convective cell characteristics. These are the normalized frequency distribution. First one is lifetime for greater than 30 dBz. Here I say lifetime, but I focused on the strong reflectivity region time only, 30 dBz, which is intense precipitation already, not cloud lifetime. So when looking at lifetime for 30 dBz, there is no significant difference. Most of convective cells less than 60 minutes in a time. Maximum reflectivity, no significant difference. Some convective cells has a stronger reflectivity for high aerosol environment, but it's basically almost same distribution. These are ecotop height, 30 dBz ecotop height and 50 dBz ecotop height. No significant difference in 30 dBz ecotop height, but 50 dBz ecotop height is slightly higher for high aerosol environment, as you can see here. These are GDR top height and KDP top height. No significant difference in KDP, but there is some small difference in GDR top. As you can see, higher GDR columns suggesting deeper convection for high aerosol environment. So I can see clear difference in this normalized frequency distribution. But when we look at the time series of these radar parameters, we can see the clear difference between low aerosol environment and high aerosol environment. These are the height versus time cross section of radar reflectivity on the top and GDR on the bottom. These are composite plot of all of convective cells. And center of each panel represents the time of maximum 30 dB ecotop height. So we can see some characteristics in the shallow convective region, convective period here, and then after mature stage in the right side for each plot. As you can see, both environments show the similar reflectivity pattern, but for high aerosol environment, you can see some higher reflectivity extended a little bit higher altitude compared to the low aerosol environment, but the pattern looks similar. But GDR shows this clear difference. As you can see, the higher GDR for high aerosol environment at a given time. And the large GDR is particularly lower altitude below 5 kilometer altitude. This should be corresponding to raindrop size distribution. So these are the same height versus time cross section for rain D0 on the top and W number concentration on the bottom. High GDR sure corresponds to the large raindrops below the melting layer. Yep. And these are corresponding to the lower number concentration compared to the low aerosol environment. These differences particularly clear in the early stage before approaching the higher cloud top height. And also large D0 region little bit extended to the higher altitude until the melting layer. Interestingly, these characteristics are correlated with the global evolution. The bottom two plots show the time series of global region estimated by polarimetric radar measurement. As you can see, when the volume of global region increases, D0 increases, suggesting some role of globals on the particle raindrop size distribution in the lower altitude. But observation is limited to interpret the process of the particle size distribution. So I used the model simulation using RAMS simulation. RAMS is developed by Colorado State University, and then settings is here. We run the RAMS for the six Houston cases. Horizontal resolution is 250 meters over this region, over the Houston area. Microphysics is about 2-moment bulk microphysics. And we simulated different aerosol initialization. Clean environment is 10 percentiles based on the observation. Polluted environment is 90 percentile of aerosol based on the observation. Once we got the output from RAMS, I applied the radar simulator to simulate the radar reflectivity and other polarimetric radar parameters. And the radar reflectivity is converted to the two-dimensional variables, vertical integrated liquid parameters here. Using these 2D variables, I applied cell tracking to collect the individual convective cells. This is an example of the result from the one convective cell study cells case. Clean simulation is on left inside, and polluted simulation is right inside. A table here shows the number of convective cells produced from each simulation. Clean on the top and polluted on the bottom. This table shows that the clean simulations produce more convective cells compared to the polluted simulations, generally 2 times larger than polluted simulations. 40 or 50 of convective cells are classified as deep convective cells. So we collected enough samples from each simulation. And similarly, this is a frequency distribution of cloud depths, 30 dBz time, 30 dBz ecotop height, and maximum reflectivity. Similar to the observation, there's no significant difference in 30 dBz time. Clean case a little bit longer time, but this is small, 2 minutes, which is less than time step. Polluted simulation have a little bit more numbers of higher 30 dBz ecotop height, meaning polluted simulation has deeper convective cells, meaning stronger updraft. But interestingly, maximum reflectivity is a little bit weaker for polluted simulations compared to clean case. And let's see the time evolution for these parameters. Similar to the observations, these are the height versus time cross section of reflectivity on the top and GDR on the bottom. for clean case and polluted case. As you can see, reflectivity evolution is very similar. Or even clean case shows a little bit stronger reflectivity. But GDR is opposite. As you can see, clean case shows smaller GDR, and polluted case is higher, larger GDR, particularly below the 5-kilometer altitude, which is a freezing level. This is representing difference in the particle raindrop size distribution. These are the same height versus time cross-section of median volume diameter D0 on the bottom, on the top, and number density on the bottom. It's clearly shown that the clean case has a smaller D0 and higher number concentration. Polluted case has a larger raindrop with lower number concentration. Particularly, clean case has a more number concentration in the early period. And let's see the process rate from the models. These are same height versus time cross sections of the updraft on the top and the rising rate on the bottom. Interestingly, polluted case has a stronger updraft at the given time, especially in the middle of the time. This is about 15 meters per second. In response to the vertical air motion, polluted case also have a larger rising rate, particularly in the early stage compared to the clean case, right? So meaning there are more global by the rhyming processes in the higher altitude with a strong updraft. These are the melting rate on the top and the auto conversion cloud to rain conversion rate on the bottom. Polluted case has more melting rate in the later stage. This suggests that global particles more melted and contributed to the large raindrops in the lower atmosphere. On the other hand, clean case has a more auto conversion rate, suggesting the more collision and coalescence processes, particularly in early stage. This is consistent with a more number concentration in more number concentration in the early stage here. And okay, let's summarize in this study. I did observational analysis using radar cell tracking radar data in the Houston for deep convective cells. Deep convective cells has a large GDR in early stage, which correspond to increase in rain D0 and decrease in rain NW. These are correlated with the evolution of global. This difference is particularly clearly found in high aerosol environment. Okay. The Ramos simulation shows a consistent result. And further, the Ramos simulation helped to better interpret the observation. Melting global particles contributed to large raindrops for the polluted simulation like this. On the other hand, collision coalescence dominate for rain formation in clean environment convective cells. That's all. Thank you for your attention. Any question?
Thank you, Mariko. Your research spans various disciplines. I expect some questions. Maybe students first. Very nice talk. Foundation students to the front.
For the simulations of the radar, is that like a constant altitude radar projection, or does it replicate scans
Oh,
like the next drive does?
that's a good question. I just applied to the constant Cartesian grid,
Okay.
not consider the strategy scans.
Anyone else? Any questions are allowed, especially from students? Maybe a quick question in between from me. You showed the SMPS. Well, you showed the particle number concentration. That's the ground measurement. Is there measurements maybe at a higher altitude
Yeah,
available? Because I mean, of course, it's a strong convergence, strong updraft, but of course, one could say, does the number concentration you measure on the ground, is that the same as at the cloud base, for example?
yeah,
You get the whole boundary layer, and maybe you get even more, even in the clean case, a bit more aerosols. And in some cases, you didn't see one of your slides where you looked at cloud echo, cloud top height echo signal, etc. You didn't see so much differences. And I was wondering, maybe the actual aerosol number going into the cloud is a little bit different than what you measure on the ground, or even the aerosol size.
Yeah.
Is there more data available maybe?
yeah, that's a good question. That is the issue that I was struggling. Yeah, this is the field campaign is naming aerosol convective study, but we have the SMPS at ground base that only available for my analysis. There are some Pavlos did the aircraft measurement with the in situ aerosol measurement, but sampling is not enough for my simulation, my analysis. My analysis is focused on the statistical characteristics of many convective cells, even only 100. But from June to September, but Pavlos in situ measurement is also good, but for very specific convective cells. So I didn't use that case. We may be able to use some LiDAR measurement, that it's difficult to do quantitative estimation.
Yeah, so are the simulation cases the same as the observational cases?
Yes, mostly same. I collected some convective cells from several very large period from June to September. But simulation cases is some 6 cases from those periods. So some of are overlapping, some of them not.
So then I believe the meteorologists are also different.
Yes.
Right, between the cases.
Right.
With the simulation, then you will be able to keep the meteorology the same, but the aerosols different. Won't that tell?
Yeah, that's a good point to discuss. We selected 6 cases, which all are isolated convection associated with some sea breeze cases, but some mesoscale methods could be different. But I checked each case with different also impact, but all the same tendency, show the same tendency. Yeah. But some more detailed mesoscale should be discussed later.
So have you thought about using the same meteorology from one case, but take a different aerosols?
Yes,
That would give a cleaner
right,
answer.
right. The setting, we simulated the clean version, polluted version for each
Oh,
case.
okay, each case,
Okay.
okay.
But initialization, the aerosol number concentration is also different with case because it's based on the observation. Like I say, 10 percentile of aerosol concentration for clean, 90 percentile of aerosols for clean. The percentile is different with the case.
Thank you.
Yes, please.
Yeah, so I'm not sure if I remember correctly, but in your clean cases, you have more deep cells and less shallow cells. And in the polluted case, you have more shallow cells and less deep cells. And no matter how that fit into the in your when you study the deep cells in the polluted case, the deep cells grows higher than the clean ground.
So your question is the number of
Yeah.
convective cells? Yeah, that's a good point too. First, for observation, we track the one convective cell at one time, and then criteria of the little bit biased. For example, we more focus on deep convective cells we track. So when we tracking the convective cell, so meaning we more try to choose deep convective cells rather than the shallow. So there are some bias in the observation. Yeah. But simulation is no bias. It's really the number of cells. It shows some aerosol impact. It's interesting.
Can I, Shen, please.
Very nice study dealing with a very challenging problem, right? So I was wondering, can you do anything for mixed phase zone within the deep convective clouds? Because a lot of aerosol cloud interaction from theoretical point is focused on the mixed phase zone in terms of the convective one. That's first question. The second one is dealing with updraft, right? So the updraft is challenging part and also associated with a lot of latent heat release. So with your multi-radar configuration, right? You have some insight into difference in terms of updraft.
Yeah, both are very difficult questions for me. The first question, it's a question for me too. You say anything and what we can do. Mixed phase is a very difficult part, both in terms of observation, in terms of processes. From the radar perspective, which is my area, mixed phase is a very big uncertain for retrievers. Vertical air motion, particle force speed, particle size, everything. So in this case, I avoid that phase, but my question is, what can we do for using radar and remote sensing measurement? For you. Second question. Yes, that's my part of my my study. I am doing the multi-Doppler radar retrievals because we have two radars focusing on one convective cells, and this can give better estimation of vertical air motion. But I would say the sample size is not enough. I applied my Doppler velocity measurement for only 8 cases, 8 convective cells. No, not convective, 8 storms. So far, not enough. I tried to do some impact of aerosols, but I don't see strong, clear difference so far. So that's now I'm working on the modeling here, but vertical air motion estimate is my next step study.
Yeah, thank you.
Okay, Malcolm, please.
Well, thank you for a very interesting talk. Firstly, an apology. I'm an oceanographer and know next to nothing about cloud physics, but I learned a lot. But I didn't know what a Gropal particle was, so I looked it up on Google Gemini, and it explains to me what it is. But it says sometimes that form into conical, spherical, or conical shape. How could nature make a conical Gropal?
Oh yeah, that is my another interest too. So I like polarimetric radar measurement. Basically, conical global first, like this shape, right? Vertical axis is longer than horizontal axis, basically. I know not always. many studies show the negative polarimetric variables for global region. Negative polarimetric variables means particle shape is like Polaroid shape. It could be associated with conical global shape. In some cases, have a positive or very small value of the polarimetric variables, which could say like a little bit more spherical shape of spherical shape of global particles. But this is what we can do so far. But it's my interest.
Well, I had maybe allow me one quick follow-up question because I'm an ice nucleation person. And since you said statistics, you have the size distribution on the ground. Maybe you have composition too, I don't know, on the ground. But in the polluted case, you showed you have in principle more rhyming, larger raindrops, but all the rhyming and everything depends how much primary ice nucleation you do up there. So you could maybe look at your size distribution. Folks would suggest ice nucleating particles are above 500 nanometers. And if you have all this data set, all this long-term data set, and CCN, as you all know, starts at 50, 70 nanometers. So they're much smaller. So you can take two pots in principle, two sources, and can look at some storms if you have more particles above 500 nanometers, just statistically. And if that correlates with your polluted case more, because if they go up and it's insoluble material, they will promptly nucleate. The beauty is with these storms, in principle, you don't need someone like me. I always joke that the updraft is so fast, you reach so quickly supersaturation, everything nucleates. I mean, a plane will nucleate, or 15 meters per second. You throw a piece of paper up there, everything nucleates. So in principle, in 15 meters per second, you reach such high supersaturation with respect to ice so quickly, you don't need to really care about that ice nucleation physics. Maybe I take that back in 5 years, but I just say that now. So if you do mixed phase cloud or cirrus like I do, you deal with 0.1 meters per second to 1.5 meter time, and things get really difficult. And it sometimes takes half an hour till reaching really high supersaturation on the cirrus clouds. But in those, in 15 meters, I mean, you can make ice in your refrigerator because of all these factors. And so it's no art, I think, to make ice in these clouds. The question is how much ice you make. And that could, maybe you can see a correlation, how many larger particles you get into the cloud. So not just look at the numbers or say everything above 50, but then say, okay, I split it up, everything above 500, which storms or convective systems has more? And does that correlate with your rhyming or Kraupel signal? Just back on the envelope, all right? This is, of course, without any microphysics, but if there's an indication, then you could relate your aerosol source, your polluted case, even with a rhyming case.
Interesting to.
Yeah. So
Yeah.
you don't need me. Simple. You just switch it on. No. Okay. Anyway, that was. If there's nothing else anymore, of course, then I invite everyone for lunch in the Svensson room as usual. And thank you very much for this really nice talk.